Hello, everyone. This is David Fenella, Senior Director of Engineering at the Concrete Reinforcing Steel Institute, and I'd like to welcome you to our webinar today on our new seismic design guide. Before we get started, I wanted to just go over a few little items about our GoToWebinar platform, in case you may not have used this particular platform before. So, the audience controls are located in the GoToWebinar control panel, and this panel must be expanded in order to see the available drop-down options. The control panel includes a button to change the presentation to full screen and also has drop-down menus for the presentation handouts, which you'll have two of, which I'll talk to you in a second about, and also to submit any questions. So if you have any questions, put them in the question box and I'll get to them at the end of our presentation today. Now, the handouts, you should have one PDF that has all of our slides for today, and the other PDF gives you the complete table of contents of the seismic design guide, as well as the first chapter. You know, in our 1 hour time, we're limited in terms of what we can go over, so this will give you guys more information about some of the more specific things which are in the design guide. Now, support is available by clicking the Help button located at the top of the GoToWebinar window or in the menu bar, depending on what platform you're running the system on. So, given that introduction, please put any questions, like I said, into the question box, and we'd like to get started today. So, what we plan on doing in our 1 hour session is to go over each of the chapters that are in the seismic design guide to give you some key information in that chapter, which I believe will be useful in your everyday work. There's a lot of good stuff we have packed into this design guide, and I'd like to point out some of the more interesting things, some of the more useful things as we go along. In addition to that, I would also like to go over some of the major code changes that occurred going from the 2014 to the 2019 edition of ACI 318. There are quite a number with respect to seismic design, especially for the special structural wall. So we'll spend a little time on that. So given those two main objectives, we're going to go ahead and first give you a general idea of how the design guide is organized and then get specifically into these two topics. So this is our latest design guide from CRSI. It came out last month. And I want to make sure everyone's clear about its overall scope. This design guide focuses on cast in place concrete building structures with non-pre-stressed steel reinforcement. So if you're interested in any post-tensioning or precast or anything of that sort, our sister organizations would be able to help you with that. They have a lot of resources that you can go to PCI and PTI to get information on those types of construction. So just so everyone's aware, cast in place concrete buildings with non-pre-stressed steel reinforcement. I also wanted to make sure that everyone realizes we cover all seismic design categories in this design guide. So from B all the way up to F. And we give complete information about all of the design and detailing requirements for all the different seismic design categories. So if you're working in particular areas of the country, which may not be the highest seismic, this design guide still has you covered with all of the requirements that are needed. We've organized it with respect to seismic force resisting system, as you'll see here in a minute. In each chapter, for each different type of structural element, there are step-by-step design procedures that we list out similar to what you would have in a flow chart. And then we use those design procedures in the worked out examples so you can follow along and not miss any of the important requirements that are in the code. There's a lot of details, a lot of design aids, a lot of worked out examples. We put an emphasis, like we do in all our publications, on constructability. but even more so, as you might imagine, especially in the higher seismic design categories, where you need to make sure that everything is going to fit properly within your section. So here are the chapters in the book. And like I said, other than the first chapter, which you have a copy of in your handout, and we're not going to go over the appendices, that just gives you some information on the steel sections and such. We're going to briefly go through each of these and highlight both the key information that's in that chapter, as well as the major code changes that occurred going from 2014 to 2019 edition of ACI 318. So we're going to start with chapter 2, seismic design criteria. And the information in this chapter is basically what's in chapter 11 of ASCE 722. So the publication is based on the 2022 edition of ASCE 7 and correspondingly the 2024 edition of the IBC. So all of the seismic ground motion values, if you're not aware, in ASCE 7, in the latest edition, there is a multi-period design response spectrum that is now available to use. And you can see that here on the right-hand side of the slide, where we have on the horizontal axis, the period of the building, and on the vertical axis, we have the design acceleration. And that design acceleration is going to be used in the determination of the seismic base shear. Okay. Now, there's also as an option what we've had in previous editions of ASCE 7, the 2-period design response spectrum. That's still available. Any and all of that information can be acquired in the ASCE 7 hazard tool, and that's free to use. You input either the latitude or longitude, the street address, or the actual point and click on the map for your particular site, and all of this information will be given to you, as well as these 22 points in different formats, including an Excel format, so that if you want to take those accelerations and put them in as input in say a modal analysis, which we did in a few of our examples here, you can do so. And you can also plot it, like we have here. The program plots it for you, but you can do it as well. So that's given in chapter 2, all of the information on how to determine this, as well as a design procedure for how to determine the seismic design category. Okay, all worked out. So let's move on to chapter 3. Chapter 3 covers the seismic design requirements for building structures. And this is basically all the information in chapter 12 of ASCE 7. So we go over all of the different types of seismic force resisting systems for reinforced concrete structures, including a new one, which we're going to go over. We talk about diaphragm flexibility, making sure we understand that reinforced concrete diaphragms are not always rigid. When's the good time to use a semi-rigid diaphragm? We go over all of the irregularities, like the one we show here. Everything is illustrated, this type 3 vertical irregularity. We always get a lot of questions. When do you actually use the load combinations with overstrength? And this would be a particular case where you have a seismic force resisting system with a moment frame. You're transferring part of that out on a transfer beam, which are supported by columns. And what we have in this particular case, the design of the transfer beam and columns A and B must be designed using the load combinations with overstrength. So we go over that, as well as all the other load combinations that are required. Direction of loading is important. We've got very explicit figures that show when and how it must be applied and under what conditions. We give some recommendations on how to model reinforced concrete buildings. What should be the stiffnesses, for example, of your diaphragm, your beams, your columns, your walls, your coupling beams. All of that's given in chapter 3, as well as a procedure, the equivalent lateral force procedure, step by step, how to determine the forces that get applied on the building. We do modal analysis as well, in an example in the design guide. And we also give the procedure on how to determine the forces in the diaphragm as well. Chapter 4, Material Properties and Strength Reduction Factors. A few significant changes occurred here, especially with respect to the grades that are permitted to be used in certain cases. And based on that, some of the strength reduction factors had to change as well. So we'll start with concrete. This is table 4.1 in the design guide, and it summarizes for you what are the minimum values of F prime C for different applications. So a lot of this came from the IBC. Over the years, there have been some exceptions in the IBC with respect to what should or shouldn't be in ACI 318. So these foundation structure F prime Cs, as well as some of the drilled shaft that you see at the very bottom here, those basically have been around for a while. Now they're incorporated into the ACI 318. Now, because of the inclusion and the permission of grade 80 and grade 100 reinforcement for special structural walls and moment frames, we now have minimum F prime Cs for those as well. You'll notice here, the use of grade 100 reinforcement in a special structural wall, which is now permitted, requires a minimum F prime C of 5,000. That's basically because that's what the experimental tests were based on. So the committee didn't feel using something like 4,000 would be appropriate. So that's why there's a lower limit of 5,000 if you want to use grade 100 in a special structural wall. So these are important items that we need to be aware of, obviously before we proceed with design. Now let's go over some of the big changes as we had mentioned for the deformed bars. When we're talking about flexure, axial forces, or a combination of the two, and we have a special moment frame, we're now permitted to use grade 80 reinforcement in the design and detailing of those particular elements, the beams and columns in our special moment frame. What you see here below in green font in parentheses is the allowable F sub Y, or FYT, in this case would be FY, that was in the previous edition of the code. So you can see we've had a nice increase in what's permitted for special moment frames. Okay, still A706 has to be used because of its overall ductility. Special structural walls. Grade 100 is now permitted to be used. Previously, it was grade 60. This was much anticipated. A lot of research occurred between the 2014 and prior to when the work started on the 2019 edition of ACI 318 that addressed high strength reinforcement. CRSI sponsored a lot of it. There was other partners in industry that came along as well, Pankow Foundation and such. And all of this research really benefited these types of structural elements, especially when it comes to constructability. Especially structural walls with coupling beams and the congestion that might occur. So going from grade 60 to grade 100 really helps out in the overall constructability of those elements. In any other case, other than our special seismic systems, we're now permitted to use grade 100 as well. And grade 80 was what was the limit before. So you can see we've had some significant changes with respect to usage in flexure and axial force. Now for shear, same thing. Special moment frames went from grade 60 to grade 80, special structural walls 60 to 100, and that includes coupling beams in the special structural walls. Everything else remains the same with respect to shear. Now, because we went from, or I should say we've included these higher grades of reinforcement, we needed to change the upper limit for tension controlled sections. So prior to 2019, the strain in the reinforcement farthest from the compression face had to be as a minimum 0.005. Okay, where did that come from? it's the strain in the concrete, which is 0.003, plus F sub y divided by E sub S, the yield strength divided by the modulus of elasticity of the steel. And if you do that for grade 60, it works out to be about 0.002. So that's where the 0.005 came from. Now, with the inclusion especially of grade 100, that really didn't make sense anymore. So now tension control section is defined as which epsilon T has to be at least epsilon sub Ty plus 0.003. Okay, so this is our new limit for a tension control section. Beams, slabs, all of those have to be tension controlled, but where we could use basically phi equal to 0.9 is now limited by this equation here. Okay, let's move on to chapter 5, bearing wall and building frame systems. We cover seismic design categories B through F. Design categories B and C, we're required to use only an ordinary structural wall. There's no special detailing involved in that. The way these are detailed are believed to provide sufficient ductility for these low to moderate seismic events. In seismic design category D through F, we require special structural walls, and the new system that I had mentioned before, this ductile coupled wall system, is also now available. And we'll talk about that in a little bit. So let's go through some of the major changes that occurred for special structural walls. These are all given in section 18.10 in the ACI code. We're going to start with longitudinal bar termination. So we have this structural wall supported by this foundation. Again, it's basically a cantilever wall, and we'd like to cut some of the longitudinal bars off where we don't need them anymore. So we've labeled those as the A bars here, okay? So from the moment diagram, we can find out theoretically, we can cut those bars off and the wall would be adequate for flexure and axial load at a distance of H sub cutoff from the critical section, which is the top of the foundation. Now, the new provisions in section 18.10.23a tells us that we can cut those bars off 12 feet above the theoretical cutoff point, but they don't have to go any further than a tension development length above the floor that's immediately above the theoretical cutoff point. Now, in this case, you can see that would be the situation. L sub D brings us to a lower value for the overall total cutoff length. And that really improves things, because if you're familiar from the previous editions, that cutoff, that additional length had to be 80% of the length of the wall. So for relatively long walls, you were talking about bars that would have to go sometimes 2 or more stories above where they theoretically had to be cut off. And this, again, based on some research and some analytical work, gives us a much reasonable determination of where we can terminate longitudinal bars over the height of the wall. Now, go into the B section in that section in ACI 318, where locations where yielding is expected to occur, that tension development length has to be 1.25 times the specified yield strength of the reinforcement. Okay, why is that? Most likely the actual yield strength is going to be greater than the specified value. There's strain hardening that needs to be accounted for, as well as cyclic load reversal. So anywhere where yielding is likely to occur, we have those values, those regions defined for us in the code. We have to determine our tension development lengths based on 1.25 times F sub y. Lap splice locations. These have been reworked as well. So we've got our same wall back here again. We have the critical section located at the top of the at the top of the wall. Oops, sorry about that. And what the code tells us is that lap splices in elevation of the wall are not permitted in the first 20 feet above the critical section. I should say the story height of H sub X, but not more than 20 feet above that critical section. So lap splices are not permitted in that region, as they are not permitted a tension development length of L sub D into the foundation. Okay, as we know, these lap splices, when subjected to relatively large compressive forces, are not going to perform very well. So in elevation, not permitted in the first story height, H sub SX, or 20 feet, and L sub D below that in the foundation. Now in plan, just waiting for the slide to change in your view. In plan, they're not permitted in the grayed out areas that are shown here as well. So that LBE is the length of the confined zone, the boundary element at the ends of the wall where we expect very large compressive forces. So in both directions. And then we also have this junction here where we have our T section where they're not permitted as well. So in any of those gray areas in elevation and in plan, lap splices are not permitted. Now in section 1810-24A, we now have new minimum longitudinal reinforcement requirements at the ends of the wall. Recent earthquakes and recent research has shown that relatively thin walls with relatively small amounts of longitudinal reinforcement at the ends of the wall have not performed very well. A lot of them have buckled under the compression force, severe cracking and buckling. So for walls that have a height to length ratio of at least 2, which typically tells us that these walls are going to yield, flexural yielding is going to occur. The walls are continuous from the base to the top, and it has a single critical section. What we are now required to do is provide a minimum amount of longitudinal steel within these distances here indicated in ACI figure R18-1024. So that reinforcement ratio, which would be the area of steel in these shaded areas divided by the area of that shaded area, has to be at least 6 square root of F prime C divided by F sub Y. Now, if you look at the elevation of the wall, that occurs not only in plan over that distance of 0.15 L sub Y, but it also occurs over the height of the wall. The greater of the length of the wall, or M sub U divided by 3 V sub U. Okay, that's your classic, if you want to call it, plastic hinge region. So within that region, both in plan and in elevation, we have to provide at least that 6 square root of F prime C over Fy. What we did here in the figure in the design guide, we just worked it out in terms of area, and that's how much area needs to be provided in both of those regions. But again, it's only for the case where the height of the wall is greater than or equal to 2, and it's continuous from the base to the top with that single critical section, which typically occurs at the base of the wall. All right, probably the most significant change occurred with the determination of the design shear force, which is now called V sub E. As we know in our special moment frames, when we design the beams and columns for shear, we design them based on the probable flexural strength of the member. In other words, what's the largest moment we would anticipate that to occur? The reason we do that, we want the members to yield in flexure before they would fail in shear. Now, in the 2014 edition of ACI 318 and in previous editions, that's not the case for shear walls. V sub U that we designed our walls for was based on the prescribed loads in ASCE 7, which, as we know, are artificially low. So in other words, we were not designing these walls to ensure that flexure would govern over shear. So to account for that, we had to come up with some new requirements here that will ensure that this ductile flexural yielding occurs prior to shear failure. Now, this method's been around for a number of years, and it's in the Structural Engineers Association of California Blue Book. And it just was first introduced into the 2019 edition of ACI 318. So this is what we're typically looking at here. When you apply the code prescribed seismic forces to your wall, you get V sub U and M sub U at the base, which we know is smaller than what you would anticipate in the actual earthquake. So you could draw your shear diagram, you can draw your moment diagram. What we would like to do is to design the wall for MPR for the case of shear. So by doing that, that will increase our shear force from V sub U to V sub E. That's the same as if we increased an additional, added an additional seismic force to the actual forces to develop MPR at the critical section. So what the equation looks like in section 1810.311 is what you see here at the top of the slide. V sub E that we need to design the wall for, special structural wall or shear, is this capital omega sub V, this is an overstrength factor, lowercase omega sub V, this is a factor that accounts for higher modes of vibration, and then V sub U, which is the factored shear force that we obtain from analysis from the code prescribed forces. The upper limit on this is 3 times that V sub U. So how do we determine these omega factors? You go to ACI table 1810.312 for the case of omega sub V, which is defined as the overstrength factor at the critical section. For the case of when we anticipate flexure to control over shear, which is defined here as the height of the wall above the critical section divided by the length of the wall greater than 0.5, it's the greater of the probable flexural strength of the wall divided by M sub U, or 1.5. If the wall's going to likely fail by shear first, like a low squat wall, then we don't need to consider that overstrength factor. Now, lowercase omega sub V is the factor that accounts for dynamic shear amplification, the higher modes of vibration. These equations, again, depend on the height to length ratio of the wall. N sub S is the number of stories that are in your particular structure. Now, you can see again, when the height to length ratio is less than 2, we don't need to consider this. Now, it can be a lot of work to determine all of this. Okay, this omega sub V isn't all that difficult to determine. But if we go back to the slide that shows the calculation of capital omega sub V, MPR depends on the axial force that you have in the wall for the load combinations that include seismic. So, you've got to do this for 2 load cases, determine that MPR. And I could tell you from doing quite a number of these walls, what I would certainly recommend, at least in your first pass, is to design the wall for 3 times V sub U. More often than not, when you go through all of the work and calculate MPR and then include the lowercase omega V, it's more than likely going to be larger than 3 V sub U anyway. So if you start out with 3 V sub U, you know you're going to have a really good wall design based on the new provisions. So just something that I've, came across by working quite a number of these different situations. So that would be my recommendation to you in this case. Now, along with that came some detailing requirements. I'm not going to go over all of it here, but one thing for sure is that, again, based on experiments, they found that this region where we have our confined part of the boundary element should be limited to a length to width of no more than 2. Okay, when it starts to become longer than that, it doesn't perform as well as one where it's limited to 2. In cases where you must have something that is greater than 2, what you need to do then is to overlap 2 sets of this transverse reinforcement and have those limited by 2. And they give some requirements for the length of this overlap length, I should say, as well. So this S sub over. Okay, so that's a detailing requirement you need to be aware of, as well as when you're in the region where flexural yielding is likely to occur, all of the longitudinal bars in the web of the wall have to have transverse reinforcement around them, and they have to have 135-degree hooks at both ends. Now, that's probably not the most constructible thing to do, although there are contractors who tell us it's not a big deal, but know that over that length of either L sub W or MU over 4VU, you've got to have these cross ties around all of the longitudinal bars in the web. Now we show here one wall that has 90-degree hooks, another that has the headed bars. Those don't necessarily have to go with one or the other. There's just for illustration purposes, they can be used in any situation. Now, what you see on this slide and the previous slide is one figure in the design guide where it gives you all of the requirements in one place for the length of the boundary elements, the minimum width of the flexural compression zone. There's some new stuff in here as well. Transverse reinforcement around the boundary elements. What's the spacings horizontally and vertically? What's the required area? Here's that hoop overlap I was talking about. Here's the requirements for the cross ties in the boundary element, as well as the transverse reinforcement in the web. So it's all summarized in one particular spot. Now let's move on to this new system, the ductile coupled wall system. Prior to the 2019 edition of ACI 318, as well as prior to the 2022 edition of ASCE 7, there was no way to distinguish between a wall that was not coupled and one that is coupled. Okay, the coupled wall is illustrated here in this figure. Now, the coupled wall performs significantly better than an uncoupled wall, but there was nothing in the code that permitted us to take advantage of all of that additional benefit. So a new system was created, which is called a ductile coupled wall system, which consists of special structural walls and coupling beams that have specific requirements that go along with each that we're going to cover next. Now, there's height limits for this system, but there's also a minimum building height of 60 feet. And the reason for that is anything less than that, you're not going to achieve the ductility that would be needed to come up with what's anticipated for this particular system. There was a FEMA P695 study done. If you're interested in that, you can go to the Pankow Foundation website and download that report for free. You'll see in ASCE 7 that the response modification factor for this system is 8. Omega sub 0 is 2.5, and the deflection amplification factor is 8 as well. So it's a very ductile system. We've got a number of examples in the design guide that show the design and detailing of this, and we pair it with a system that's uncoupled so that you can see exactly what the difference is. You know, this couple that forms at the base significantly relieves the walls of moment, and you know everything's taken up pretty much by the shear in these coupling beams, and that's what dissipates the energy. So what are the individual requirements for both the walls and the coupling beams? For the walls, they must have a height to length ratio of at least 2, and they individually must be designed and detailed as special structural walls in accordance with Section 1810. So there's really no big extra detailing that goes along for this particular system for the structural walls. And that also can be said for the coupling beams. As long as you satisfy the geometric requirements that are shown here, as well as ensure that the reinforcement is developed for 1.25 times F sub Y, and you design it and detail it just like any other coupling beam in accordance with Section 1810.7, you have a ductile coupled wall system which can utilize that very large R value, your response modification coefficient. So it's a great system to use, especially in higher seismic regions. And the nice thing about it is because of the overall height, clear height, I should say clear length to height ratio, we can design these coupling beams as if they were special moment frame beams. In other words, we don't have to put the diagonal bars to design and detail these. So that in itself is great for overall constructability. You'll notice down here, it kind of gets lost, but we talk about it in the design guide. Another constructability issue, you know, keep in mind, we've got all of these bars at the end of the walls from the wall boundary reinforcement. So we'd like to push the longitudinal bars in at least about 3 inches so things start to clear one another at the joint between the beam and the wall. So there's a lot of little stuff like this all through that will help in terms of your overall constructability of these structural elements. And speaking of that, just wanted to show a couple slides. You know, take a look at the plan view of the structural wall. We have a coupling beam, we have floor beams framing into the wall. There's a lot going on in that joint where everything is intersecting. And needless to say, you know, taking a second, third look at your bar size and spacing to make sure you have enough space to get the concrete in is certainly an important thing to do in this particular case. Just something else that works not only for higher seismic design categories, but every seismic design category. How many of our typical details for a wall at the top floor where the longitudinal bars get hooked in to the slab? Those can cause you some problems sometimes, you know, with tolerances and constructability. So what we recommend is if you don't have it already, you know, try using a dowel bar that can be easily adjusted so that we don't run into any issues with the slab bars that are up there at the top of the slab. Same thing when you have corners or any other type of joints. We highly recommend that the horizontal bars do not have hooks at the end of them in the wall, especially if you're going to use pre-assembled cages for the wall reinforcement. Those hooks can cause huge problems. So if you supply these extra bars that can be threaded in later, that will help in the overall construction of the wall. Now, the examples we cover here from, again, B through D, bearing wall systems, building frame systems with ductile couple wall, that's shown here. So in the north-south direction, we've got them coupled. In the east-west, they are not. You can see a really good comparison of how these two systems respond to the seismic forces. And we also have the case where we do a modal response spectrum analysis for this system as well. So we covered a lot of stuff in that chapter. There's not that much additional to cover in the rest of them, except for what we're going to show here. It's not going to be of the same time length, I should say. Chapter 6, we have moment resisting frames, ordinary, intermediate, and special. One thing that we did here is put a design aid together to help determine what that minimum joint size should be. You know, especially for special moment frames. You know, everything's driven by that joint in the special moment frame. And typically what occurs, you have a nice design for everything. You come back and check the joint and it doesn't work. And you have to start all over again. So what we did is we took the basic joint shear strength equations for all the different cases where a column is continuous, where it's not continuous, where a beam is continuous and not, and if you have confinement in the perpendicular direction or not. We came up with a number of different charts that, depending on how much longitudinal reinforcement is going through the beams, which, as we know, that's what's driving the shear force in that joint, what the ratio of the column area to the beam area needs to be for different compressive strengths of concrete at different yield strengths. Okay, we typically recommend using a 1% reinforcement ratio for the beams. And if you do that, you'll see that depending on, again, what type of confinement and what joint type you have, it'll fall within this range here. And we tested it with a number of different cases and it works out pretty well. It gives you some very good estimates of what that joint needs to be in order to satisfy your joint shear strength criteria. Then you could take that, put it into your model, you know, check overall deflection, sway, and such, and see if it works out okay. And again, it'll work. It usually does. Of course, everything is different, but it's going to get you in a very good place to begin with for that joint. I did want to also show you, we have these tables of guidelines and recommendations for details. So this is the one for special moment frames. So, for example, space the laterally supported longitudinal bars in the columns no more than 8 inches on center to increase hoop spacing. Again, helping with constructability. And you can see the explanation behind it here. So we have it for all the different systems, you know, towards the end of the chapter. You know, if you take these into account as you're designing and detailing, hopefully it's going to decrease your RFIs in the long run. In this chapter, we have examples that cover ordinary, intermediate moment frames, both a flat plate, which is permitted to be used, and then a special moment frame for seismic design category E. Chapter 7 covers dual systems. These are typically used in seismic design category C and D. And these systems are made up of structural walls and moment frames, and they're designed to resist the seismic forces in proportion to their rigidities. One other very important requirement is that the moment frames must be able to resist at least 25% of the seismic load effects without the walls. So these frames provide a good backup for the walls and are able to support the gravity loads in case anything, you know, detrimental were to occur in the walls themselves. Now, I could tell you again, by doing, I should say, a number of these different examples, quite a number of them, that when you go ahead and design the beams and frames, beams and columns, I should say, in the moment frames, this particular load combination is the one that usually governs. So the examples we have here in seismic design category C, it's a dual system with an ordinary reinforced concrete structural walls and intermediate moment frame. And in seismic design category D, it's a dual system with both reinforced concrete ductile coupled walls special structural walls, and special moment frames. So this gives you an example of this of the floor plan we have in this particular example for seismic design category D. In the north-south direction, we have the coupled system in combination with the moment frames. And in the east-west, we have just the special structural walls in combination with the moment frames. And again, it illustrates what the big difference is between the dual system and the system that utilizes just the walls in combination with the frames. Now in seismic design category B, we use a shear wall frame interactive system. And it's basically the same as a dual system, except everything's ordinary here. So ordinary structural walls and ordinary moment frames. So we've got an example that illustrates that as well. Chapter 9 covers diaphragms, and that's again through seismic design categories B through F. This just shows you one of the examples where we go ahead and determine all of the unit shears in the diaphragm and in the wall. We get our unit shear forces, our net shear forces, and what our collector forces is. We do it for quite a number of different examples of the buildings that we covered before. We have also these tables and figures that illustrate all the different types of reinforcement. For the case where we have collectors that are the same width as the vertical element of the lateral force resisting system, as well as collectors that are wider than that. And what are all the details, where you could find the equations to determine all of that reinforcement. Two different type of construction methods that we go over depending on where the cold joint occurs and how to determine all the different reinforcement in the diaphragms. And our examples cover both seismic design category B and D. Now there's one really interesting one we did for seismic design category D. It's a building frame system with a horizontal irregularity. And this is the floor plan at the elevation where the horizontal irregularity occurs. So you'll note here along lines B and E, structural walls that are coming down from the top of the building. Those then at this particular level are getting transferred out to walls A and walls F respectively. So this diaphragm between lines A and B and E and F need to be designed appropriately for the shear that's coming down from those shear walls and getting transferred out. We go through all the design and detailing. This is a perfect example where in your computer software, you would assign the diaphragm as semi-rigid. There's really no other way to get the proper representation of the shear transfer in these particular cases. And I just wanted to show you the very last detail that's given in that example where we have the wall on the beam, everything here. Obviously the collector is going to have to be much wider than this 12-inch wall that it's framing into, and that's all illustrated here. We distinguish the different bar types by using a gray shading for those bars. Chapter 10 covers members that are not designated as part of the seismic force resisting system. So again, this only comes into play for seismic design category D and above. Beams, two-way slabs, and columns. We go through all of the requirements for all of the different cases and provide figures such as this that show you what you need to do in those cases. Finally, Chapter 11 is devoted to foundations. Footings, mats, pile caps, grade beams, seismic ties, piles, and drilled piers. We'll just touch over some of the major changes. Now, this is a new table 18.13.571 that's given in ACI 318.19. And a lot of this information came from the IBC. It's applicable to uncased, cast in place, drilled or augured concrete piles or piers, sometimes referred to as caissons. So you can see it's broken up into the case of where you have seismic design category C, regardless of what the site class is, and then D, E, and F, and that depends on what site class you have. Minimum amount of longitudinal steel. What's the minimum reinforced pile length? What's the transverse confinement reinforcement zone, its length, and how much reinforcement you need there? So this is a lot of new design and detailing that we're required to do. So what we decided to do is take the information in this table and illustrate it in a number of different figures so that you can visually see over what lengths reinforcement is required for cases when you have hard or stiff soil over the entire length, or as shown here, what if you do have a liquefiable or soft soil layer to account for? How do you provide the proper detailing for this as well? So that's all covered. This is in particular for seismic design category C. We have it for D and above as well. Last thing we'll talk about here before we get into some other resources that are available, we go through a complete example of an isolated spread footing for moment frame and seismic design category E, drill pier and grade beam, and drill pier and pile cap. You don't see design to pile caps often enough in a lot of different places. We do have a design guide that covers it, but not for seismic in particular. So we have done things in this particular example you're not going to see anywhere else. We believe it's on the conservative side. It makes sense in terms of how we applied the forces to the pile caps and such based on the general provisions that are given in our CRSI design guide for pile caps. So that particular example is the example that was given before for a special moment frame in seismic design category E. This is what it would look at elevation with the pile caps. And when you go through all the design and detailing of this, so we assume that the pile cap had a fixed head. We know what the moment is over the depth of that pile cap. And you could see all the detailing. This particular column is subjected to uplift. So we have these top bars. You'll notice we use a lot of headed bars in this case because there's certain development lengths that need to be met, especially for cases when you have tied arch behavior. And the headed bars work out very well in those cases. You'll also notice we extended, I should say, the longitudinal and transverse reinforcement at this critical section in the drilled piers up into the pile cap and tied everything together. We've got these foundation ties as well, which are grade beams, and those are all designed and detailed. The longitudinal bars have to run through the pile cap according to the provisions that are given in chapter 1813 of the code. So that gives you a whirlwind tour of our new design guide. I did want to point out a couple of other resources that go hand in hand with this in case you may not be aware of them. This publication on the 318 design guide, this design guide, I should say, on the 318 code came out back in 2020, and it's also based on ACI 318-19, covers a lot of information that's not in the seismic design guide. Okay, so that's available. We have these design checklists that are also available. What these design checklists are, and these are also based on the 2019 edition of ACI 318. These are basic information for all the different types of structural members that you can come across. And what this provides for you is, as the name suggests, a checklist that if you go through and satisfy all the requirements in these checklists, you're not going to miss any important provisions that are in the code. I can tell you I practiced for many years and I've used ACI 318 for many years. And my biggest frustration was trying to find something quickly in ACI 318 and I always worried I was going to forget something very important. So these checklists eliminate that, at least in my mind, eliminate all of those doubts about missing something important or just not finding it very quickly. So we have it for beams, diaphragms, flat plates, one-way slabs, columns, joints, walls. All of your seismic systems are there. I'm going to show you what the special structural wall checklist looks like. We also have them for foundations. So I've got to change back to my pointer here, if I can do that. All right. So this is a typical checklist. It starts out by giving you what the units are for all the equations that are given here, and it goes through all the important parts of the code that relate to that particular item. So we're with special structural walls. Here's all your material properties, your requirements. This is the ACI reference that goes with it. And here's all auxiliary information that helps us apply and understand what the requirements are. Okay, so nothing here other than what the specific requirements and the ACI references are for these particular types of elements. So material properties, minimum wall thickness. We give you an equation here you could use to find that very quickly. Here's all the ACI references that go with that. Here's the minimum wall thickness that you need to provide. Longitudinal reinforcement requirements. Here's that end wall. If you look here at the bottom left, the end wall amount that needs to be satisfied that we talked about. These figures should look familiar to you. Transverse reinforcement requirements. Now you start talking about getting into additional sections here. And this is where it can get quite dicey with respect to recalling where all of this information comes from. Okay, these should look familiar as well, how to determine your shear in the wall. We also get into your transverse reinforcement, all of the things that are required here. Okay, so that kind of gives you an idea of what the checklists are. You can use it to check someone else's work or use it as a flow chart to design and detail your particular structural elements. Now, with each of these checklists, except for members that are not part of the seismic force resisting system, for each of them, there is a Excel spreadsheet that comes with it. We call it a calculator. And I want to show you what this calculator looks like for special structural walls. Okay, so that comes with the checklist. First tab is an overview. It gives you all of the information, what the basis is for the equation, where it comes from, what are the assumptions, what are the limitations. The next tab gives you general input. General input for a concrete strength, your section. Now, what I'm showing you here is the rectangular section. We have them for T, L, and C sections as well. So you put in your wall thickness, your wall length, and wall height, and you can put up to 40 different layers of either this bar arrangement type W1 or type 2. Okay, you can see you manually input the number of bars in that particular layer for different bar size that you input as well. Now, if I scroll down here at the bottom, you recall the minimum longitudinal reinforcement requirements we covered during the hour. Those are here for you. It'll tell you if it works or not. Now, one of the powerful things that this Excel spreadsheet does for you, you can input your factored load combinations and then check to see if your wall works or not. So you can see for the loads that we have here, axial force and bending moment, everything looks okay. Everything's fallen within the design interaction diagram. This load combination here down at the very bottom may be a little too close for comfort. I'm going to go back to general input. And I'm going to change that number 8 bar to a number 9 bar. Okay, I'm going to go back to interaction diagram. I'm going to click generate interaction diagrams. And based on that change in longitudinal reinforcement, it's taken a little bit because I got a lot of stuff running here. You can see it changed, and now we've got a little breathing room for that one load combination. So that quickly, you can come up with preliminary design, check somebody else's design, and we provide here a table for you that gives you all of the key information for all of the key points in the interaction diagram. And you can calculate the value for any axial force. And what's nice, it gives you the neutral axis depth. And that neutral axis depth can be used to determine if you need special boundary elements or not. We also have a box here. If you click on calculate values for a particular axial force, it will determine what your probable flexural strength is. So that probable flexural strength can be used to determine your shear force, your in-plane shear strength, which is given in the next tab. Okay, I won't go through all of the details there, but we have in-plane shear strength, boundary elements, and coupling beams. That's all included in this particular spreadsheet. And that comes with the checklist. We have a mobile app. I think most of you may remember we have bar cards, which you can still get, but all of that information is now in our mobile app that you can download for free. Gives you bar dimensions, hook details, bar markings, rust on rebar. You wouldn't believe how many questions we get on rust on rebar, but it's all there for you. And there's a premium module for development length calculations for both ACI 318 and the 8th edition of AASHTO. So there's an Apple, an iOS version, there's an Android version as well. So even if you just get the basic information without the premium, there's a lot of good stuff there. If you are looking for any continuing education credits, we have Rebar U. We've got a lot of presentations there. You can see on this particular slide, get my laser pointer back. Here's one that we did not too long ago on special structural walls. You can access that particular recording at any time, you know, after purchase of the module. And you name it, we just about have anything you might need in reinforced concrete design and analysis. If you haven't visited our website, we've had it upgraded for a little bit now, and it's completely redesigned. A lot of good information you can find there very quickly, very easily. I recommend you go to our website. And the last thing I wanted to show you before we get into the questions I could see that are listed there, we did say we would have a discount code for the Seismic Design Guide, either the printed or digital version, and it is here for you, Seismic 15. So 15% off either the printed or digital design guide. You put that in. If you go to our website, this is the banner at the top. You either click on shop or click on the cart, and it'll bring you right there. And this design guide is probably on our front page, and you can see the information there. Certainly, if you have any additional questions, you contact me, and I'll be happy to answer those for you. Also, you know, if you think that the checklist might have been of interest to you, we have a bundle with the Seismic Design Guide and the checklists. There's all different kinds of bundles where you can save even more than 15%. So take a look at those as you browse as well. So hopefully this has been informative to you today. Let me take a look at some of the questions here, see if I can answer those. If anyone needs to drop off, we're certainly do so. Before you do, let me tell you that tomorrow you'll receive your certificate via email, as well as the link to the recording. So look for those tomorrow. All right. First question, is there a metric version? And the answer to that one is no. Unfortunately, we don't have that. We don't plan on doing any metric. Our members are here in the United States, and we have the resources to just do our US customary units. So sorry about that. Okay, next question. In the special wall section, can you please include a discussion of how to apply boundary regions, no lap splices, to typical low-rise concrete buildings? Do they apply at the edges of every door and window? There's also the likely to yield provisions. How is that determined? That's a very good question. And we do have an example for low-rise building where we've got the Swiss cheese of openings in it. What you need to be careful in those cases is it actually a wall section, or is it a pier, based on the overall dimensions of the section that you're looking at. And yes, typically you have to look at the edges of the wall as well as the edges along any openings to determine if you need boundary regions there or not, and apply the special detailing requirements. So yes, that's a very good question. And yes, that is covered in the design guide, and you do need to apply it around every opening. Next question, how available and cost effective are grade 80 and grade 100 reinforcing bars? Unfortunately, I cannot answer that for you because we're our trade association for all of our members. What I would recommend you do, contact your local reinforcing bar mill or other source that you have to determine what that would be for your particular region. Okay, slide 10. Shear stirrup and hoop is 60 KSI, and seismic in special moment frame is 80. Please clarify. Oh yeah, I think I know what you're talking about here. For shear, that's not in a special moment frame, be it a beam or column. We're still limited to grade 60 reinforcement. Reason being is basically for crack control. So that's why you're going to see the 60 KSI in your typical, other than high seismic situation or special seismic situation. That is the case. Okay, next question. Regarding the special shear wall boundary element, do we need to achieve a minimum of 1% for the vertical reinforcement in the boundary element, or should the vertical bars be designed for the entire wall? Yeah, that's a good question. Yeah, this is actually a throwback to some things that used to be done in the UBC, where you would separate out how much reinforcement you need in particular parts of the wall. Simple answer to your question is that you consider the entire wall section and the longitudinal reinforcement and how it reacts with the entire wall section. Slide 16, for those highlighted planes where splices are not allowed, does it mean the prohibited zone is only within the bottom region? Outside those highlighted regions, can splices be allowed? Yes, the simple answer to that question is yes. Lap splices are not permitted in those regions. If you wanted to use a mechanical splice with grade 60 reinforcement, you can use it in those regions. Okay, generally speaking, you're going to see construction of these walls with bars sticking up quite high above the top of the foundation, and then the other bars coming in and being tied down to those. But you can use the couplers, but it has to be with grade 60 reinforcement. Would the upcoming ACI 31825 include any further changes to the new wall design provisions in ACI 318? Yes, that there will be. I can't discuss those here because the committee has not voted them to be actual changes as of yet. Right now, they're just proposals waiting for their final vote to occur. And from my understanding, the 2025 edition will be available at least at ACI 318 plus level starting in January. Okay, one of you are having a hard time downloading the handouts. Let's see here. You know, if you do click on them, it should open up in a different window for you. See how that opened up for me when I clicked on the handout? Try it again, and maybe that'll work for you. If not, let me know, and I will send them to you. I'll send you a link where you can download them. My email address is dfanella@crsi.org. dfanella@crsi.org. Next question. Not uncommon to have a horizontal control joint between the slab and the wall. In the coupling beams, what is the best approach to address the horizontal shear transfer? Yeah, you know, that's if you could try to, well, if you can satisfy, that your typical horizontal shear transfer requirements for the interface, like you would say at the bottom, that's about the only way I could say, at least I know you can satisfy that. Having that interface reinforcement to be able to resist that can be quite a task. So if it gets to the point where you can't make it work, you may have to explore other options. I'm sorry I can't be more specific without, having a specific case to take a look at. On slide 28, could you clarify when we can only use straight bars in a coupling beam? Yes, I believe this is the case where this is for the ductile coupled wall system. You can have straight bars for the limits, the height to length limits. Let me give you the exact section number that's given in the code. Hold on one second here. So in section 1810.7.3, it said coupling beams not governed by 1810.7.1 or 1810.7.2 shall be permitted to be reinforced with either two intersecting groups of diagonally placed bars or designed as if it were a beam in a special moment frame. So you can go ahead and use those when your length to height limitations work out. And go to section 1810.7 and it shows you all the different cases, especially in the case where you do have to use diagonal bars. Okay, another good question. When will the pile cap design guide be updated for 318.19? Is it still only for 318.11? And the answer to that is we're trying to see how our resources are going to work out for this upcoming year. So I can't give you a direct answer. Just you're on our mailing list, so you'll be one of the first to know if and when that will be available. I answered the question already about the SI units. Per slide 57, there is a mobile app. That is correct. If you take a shot of that QR code, that'll bring you right directly to where you can get the app. Does the design guide provide information for the extension of ties beyond the bottom of the footing? Yes, definitely. And it all depends on how close that foundation is to the edge of the the vertical element is to the edge of the foundation. Will CRSI give webinars on the design examples? And the answer to that is yes. Those are in production right now, and we plan to have those available first quarter of next year. There will be 5 altogether, and they'll cover all the different main chapters in the design guide with explicit worked out examples. Question about the spreadsheets. If you purchase the checklists, the spreadsheets come free with the purchase of it. And there's also a really good discount if you purchase the entire number of checklists. It comes in a nice 3-ring binder, and then you get all of the spreadsheets. The gentleman who's having a hard time ordering from a particular country, contact our front desk, and her name is Allie. She's not in today, but I would try tomorrow. Allie will try to help you. If there's no way you can get a hard copy, we do have the digital version that you can purchase. There's a question, are we preparing materials on the 2025 edition? Yes. We're going to try to update all of this stuff next year. Exactly when it's going to be available, we can't say for sure. Now, there are options to purchase the guide and the checklist for a number of different computers. That's given on our website. You could take a look and see if any of those make sense. If not, let me know and we can see what we can do. In special shear wall, lap splice is not permitted in the critical zone. Can we use mechanical couplers? Yes, we certainly can. It has to be a type 2 coupler and only with grade 60 reinforcement. Oh yeah, this is another good question. How does the seismic design guide differ from I'm sorry. You know what? I'm going to answer a slightly different question than that. I didn't want that's what exactly bring other products into here. You may note that the CRSI design guide for 318 has a couple chapters on seismic design. They don't go anywhere in depth as what we have in this particular design guide. And then I could say that's true for any other resource that might be available out there. As per ACI, the maximum FY can be used for columns under the axial load of grade 80. Oh yeah, this is another good one. The answer to this question is the limitation, even if you're using grade 100 reinforcement, which is permitted, in a structural wall, do we have that 80,000 PSI limit? I would say you don't need to worry about that limit other than if the wall were subjected just to axial force, which is the case for, say, columns or any other type of structural element. Because the wall is subjected to both bending and axial force, that upper limit of 80,000 PSI does not apply. Okay, I believe I answered all the questions. If you think of anything else between, oh, okay, one more just popped up. Let me answer that one. Are the checklists specifically for seismic, or is it combined with gravity and lateral? The seismic ones are for the specific members, special structural walls, special moment frames. Those give you in particular all the requirements that need to be satisfied for their complete design. So, design for gravity, design for seismic, with emphasis on seismic. Okay, the other ones, you always go back to your other chapters. So if you're looking something specifically for beams, say other than special moment frame, then I would recommend, taking a look at the beams checklist, because there'll be more information than what's in the seismic one. I hope that answers your question. Okay, if you think of anything else, please don't hesitate to contact me. Other than that, we look forward to seeing you again in the future once we have our other seismic webinars ready to go. So I'm going to now close down the webinar. Hopefully this was useful for you, and please contact me if you have any other questions. Thank you very much for attending.